Have you ever wondered how machine learning models truly understand the world around them, making predictions that feel almost intuitive? How do they discern patterns from seemingly random information, or anticipate what might happen next in a complex system? At the heart of this remarkable ability lies a powerful mathematical concept that bridges the gap between chaos and comprehension. Probability distributions explain data generation in machine learning by providing a mathematical framework to model the underlying processes that create observable data. They capture the likelihood of different outcomes, essentially describing the universe from which our data samples are drawn. This understanding is crucial for a model to learn effectively and make accurate predictions. Data in the real world is rarely static or deterministic. Instead, it is inherently random and variable, whether we are observing stock prices, image pixel values, or human language. Probability distributions, such as the normal distribution for continuous data like heights or temperatures, or the Bernoulli and categorical distributions for discrete outcomes like coin flips or object classes, allow machine learning models to representing this randomness. By fitting a distribution to observed data, a model learns the statistical properties of the data generation process. This allows it to generalize beyond the training examples and understand how new, unseen data might be structured. Understanding these distributions helps us in several practical ways. For instance, in generative models, we can literally sample from learned probability distributions to create new data that resembles the original training set, like generating realistic images or text. In classification tasks, models often learn the probability distribution of features for each class, allowing them to predict the most likely class for a new data point. For example, a logistic regression model estimates the probability of a data point belonging to a certain class, transforming an input into an output probability between 0 and 1. A key concept here is maximum likelihood estimation, or MLE, which is a method used to find the parameters of a probability distribution that best describe the observed data. Imagine you have a set of data points, and you want to know if they came from a normal distribution or some other shape. MLE helps your model determine the mean and standard deviation for the normal distribution that would make the observed data most probable. This approach underpins many machine learning algorithms, allowing them to infer the hidden mechanisms that produced the data. Ultimately, by characterizing the likelihood of various data points occurring, probability distributions provide a principled way for machine learning models to build an internal representation of the world. This statistical understanding allows models to not just memorize examples, but to truly comprehend the dynamics of data generation, enabling them to make robust inferences and generate novel, meaningful outputs across diverse applications.